Okay, I think it did. All right, so continuing on our trend of looking at motion and specifically looking at graphs of motion, you had an activity last week where you were looking at position versus time as well as velocity versus time graphs. We're going to be throwing another one in there today, which is an acceleration versus time graph. And what we're going to be talking about is how each of these graphs can show us the same information, but can show it to us in very different ways. And then we're going to have an exercise at the end where you're going to get to look at three graphs and sort of interpret what's going along each step of the way, as well as create graphs of your own based on a narrative scenario. We're going to talk first of all about the position versus time graph. Position versus time, this shows the distance that an object is from its set starting point, also known as displacement. So on this particular little sample graph you see right here, if we put 0 kind of in the middle, then as time is flowing as we go toward the right on the x-axis, then at the very beginning right here, the object is moving away from the origin point. It's moving back toward the origin point, and it actually passes the origin point before turning back around. So any point on the graph where you have positive slope, that means that the object is moving away in one direction, the distance is increasing. Downward slope means that it's getting closer, distance is decreasing, until it passes the origin point. And whenever the object passes the point of origin, which is distance equals 0 right here, then whenever it's on, say, the negative part of this, then these two kind of flip-flop. So as you're going to find over and over again in physics, it helps to think of positive and negative as being directional. So we could define this up here as the positive direction, and moving the other way is the negative direction. It's supposed to be a D, it looks like a P. I don't know why, I'm afraid to erase. What happens when you've got, say, a point like right here or right here? What's happening where it kind of seems to flatten out? Or what would be happening if you had a distance time graph that had no slope? Yeah, staying in the same spot, exactly right. It's not moving. And okay, I think I know why this is on this slide. A slope on this graph shows you the velocity. Okay, the greater the degree of slope, the greater the velocity, and the direction of the slope, whether it's upward or downward, indicates whether it's positive velocity or negative velocity. Can anybody tell me why that peanut is there? I think it's probably because first time I gave this, somebody couldn't read my writing, and they said, why is the nut moving? That's fair. It's moving. Okay, it's moving away. It's moving toward. It's moving away. See? Nut's moving. Okay. Questions on that one? Out of the three, that's probably the easiest one for our brain to process. The next kind, and the other kind that you saw in the lab, this is the velocity versus time graph. Okay, what this shows us is the velocity, or the speed with direction that an object's moving. And so According to this graph right here, we've got, again, positive above 0, negative below 0. This object is, when it's, touching it doesn't do anything, sorry. When it starts out, the object has a positive velocity, but it's beginning, as it goes towards 0, it's beginning to slow down. When it reaches 0, it's beginning to speed up again, only it's speeding up in the opposite direction. And then very suddenly, when it gets to this point, it's going to begin slowing back down again until it comes to 0 velocity. Then it's going to begin speeding up back in the first direction it was coming from. Now, just to kind of take a look at it, compare what's happening right here in what we're going to call segment A to what's happening up here in what we'll call segment B. Okay, well, again, on this one, it's the speed that's changing. Okay? Okay, it's accelerating. They're accelerating in both cases. Which one has greater acceleration? A or B? A has greater acceleration. How do you know? Well, it has a steeper slope. It's part of it. Okay? And if you look, okay, now I like what Celeste said right there. Look at time period. Okay, if what we're looking at down here is a time period, that might be like a second or something like that. That is also like a second. Okay? Look at how much the speed changed in A. It changed 3 whole units here, whereas in B it just changed 1 unit. So you could say that the acceleration in segment A is 3 times that of the acceleration in segment B. What's happening up here in segment C? Be careful. Think before you speak. Moving at a constant speed. Okay? Is this object staying still? No, it is not. What would the graph of an object staying still look like? It would be on the 0 line. Very good. Okay. So let's jot down a few info bits about this. You got most of them. So if I have something that has a positive slope, you could say it's getting faster, but that's only if you are talking about something that is going in the positive direction. Okay? A better way to say it is what I've got over here in parentheses. It has constant positive acceleration if there's a line sloping upward. Line sloping downward means constant negative acceleration. It's being accelerated in the other direction. By the way, there's a word I really don't like. And again, maybe I'm just being picky about this, but I've heard people refer to getting faster as acceleration and slowing down as what? Deceleration. I'm not a fan of deceleration, okay? Because again, we need to be thinking in terms of direction, positive direction, negative direction. If I'm slowing down, it could be because I'm being negatively accelerated, or it could be because I'm being positively accelerated. Let me give you a for instance with my own body here. Okay? We're going to call this direction the positive direction. Call this direction the negative direction. You guys tracking? Nope. So, right now I'm moving at a constant speed, and now I'm going to speed up. What kind of acceleration am I experiencing? Positive acceleration, okay? Now, let's try again, okay? What kind of acceleration am I experiencing now? Negative acceleration. Okay. How about now? What direction am I being accelerated in? So even though I'm getting faster, that's negative acceleration. It has to do with direction. It has to, because the thing that's accelerating you is going to be a force, right? A force is going to cause you to speed up or slow down. The direction that force is being applied determines whether it's positive or negative. So who gets to decide which one's positive and which one's negative? You do. In any situation, you just say, okay, let's make that way positive, let's make that way negative. Okay? Sometimes, to do the math, it makes a little more sense. You know, if something is like doing what this just did, going up and coming back down, maybe we could define that as positive, that as negative. But we could just as easy say that's negative and that's positive. Okay. The numbers do what we tell them to. Haley Jones, you seem like you're not happy with this.
Because you had both positive and negative acceleration going this way.
Okay.
You can't have a positive and a negative.
Oh, I totally can. Ready? Okay, so I'm going to have some negative acceleration. You watching? Okay, so I'm moving. Negative acceleration. I got faster. But wait for it, wait. Okay, now watch. Positive acceleration. Because I'm being positively accelerated, I'm going this way. Now I'm going negative acceleration. Positive acceleration. See? Yes, no? Yeah, people watching this video, they're going to be like, what the heck's going on? I can't see. It's going to be okay. I can tell them. I'll dub in some video of like Mr. Bean walking or something. So, like you said earlier, if I have a horizontal line, that means I'm experiencing constant velocity. But check this out. If you've got a curve, it means that you're either having an increase or a decrease in acceleration. Okay? Which means that my rate of acceleration is not constant. Again, what I'm talking about right there has more to do with positive acceleration. It gets a little confusing. I'm not going to lie to you. If you're feeling a little bit confused, it's not just you. It's physics. In the hands of a better physics teacher, this might be slightly less confusing, but I make no promises. Yeah, well, I mean, what isn't, though?
Exactly.
There you go. All right, which leads us to the third and final type of graph we're going to look at today. An acceleration versus time graph. Okay? So this one right here you haven't actually seen. This right here tells us whether velocity is changing. So, anytime that you've got something below negative, that means that velocity is being changed in the negative direction. Anything above means velocity is being changed in the positive direction. And then if you've got anything that's on the zero, what that tells you is that acceleration is constant. Now it could be that acceleration is zero, it could be that acceleration is positive or negative, but if it's at zero, it just means that the rate that the speed is changing is not changing. It's like a little meta. Okay, there's a lot to jump on there. So whenever you've got zero, there's no change in speed or direction. If it's positive, like I said, you've got acceleration increasing in the positive direction. If it's negative, acceleration is increasing in the negative direction. Now that's if it's flat. What happens if you have curves on this? It means it's not constant. It means that your acceleration is non-constant. Okay, we're not going to worry about that. Now I want you to notice something that happens. Look at this jump from this point here in the graph to this point up here in the graph. How much time passes between those? None. It's pretty much instantaneous. So really, when you've got like these vertical lines on a graph like this, they're just there so you can have some kind of consistent path. Really, if you want to get accurate, you're not going to have connecting lines. It's going to be like an instantaneous jump. Unless, of course, you don't have constant acceleration, in which case it'll curve from one to the other. I hear you. I honestly do. This next slide is fantastic, and I should probably just print copies for everybody to keep with your stuff because it's such a good thing to refer to. So I'll tell you what, I will print a copy, and give it to everybody while you're working on the thing that I've got for you. But does anybody need anything else off the slide? Okay. So this right here is a really handy way of looking at what different things mean on all three kinds of graphs. So position graph, velocity graph, acceleration graph. Constant position looks like this on a position graph. It doesn't really matter where that horizontal line is. Here, there's no acceleration happening, and the velocity is 0. Okay? It's not getting faster or slower. Its speed is 0 with no direction. And here the position is not changing. If you have a constant velocity situation, you know the cheetah is moving at a constant speed in a constant direction, then you're going to have a constant linear slope on the position time graph. It's going to be a non-zero horizontal line on the velocity graph, and it's going to be a 0 on the acceleration graph because it's not getting faster or slower. Okay? And then last one here, constant acceleration. If I am constantly accelerating, then the rate that the object is getting farther away from where it started is going to increase geometrically. It's going to be more of a parabolic graph instead of linear. But on the velocity graph, it's going to be linear because that velocity is experiencing a constant change. It's getting faster at a constant rate. And here, on my acceleration graph, I'm suddenly not at 0 anymore. I'm going to be at either a positive or a negative number, depending on the direction that that acceleration is taking place. Okay. It's a lot to chew on, it's a lot to wrap your brain around, and that's fine, because we're going to play with it some. I'm going to give you 3 graphs, and all 3 of these graphs tell us the same story. So let me hand these to you, and then we'll annotate them. It's going to get better. We're going to park here for a while. Okay. I'm going to show no change on our position time graph, no velocity, no acceleration. Now the practice stuff on the back, don't get ahead of things just yet. I promise you we'll get there. All right. So let's start with our distance time graph, because again, that's the easiest one for our little monkey brains to get wrapped around here. And let's talk about time intervals. So we're going to talk first of all about time interval A here. Tell me some things that are happening to the object during time interval A. Okay, what is increasing? Okay, the distance between it and something else. Now, is it moving away at a constant speed?
It's got that little curve on it.
It's got that little curve on it, right? So, looking back at our cheetah thing here, what does a little curve mean on our position? Constant acceleration, okay? So this is undergoing positive acceleration, right? Now what's happening during interval B? We've now changed to a linear graph here. Is it still accelerating? It's not curving right here, is it? Say again, Nick? Okay, what's constant? Well, the distance is changing. It's still moving away. Let's go back. Constant velocity. It's still moving away, but it's not accelerating anymore. Okay, it's not moving away any faster. And so we can say, for this part in here, we've got constant positive velocity. Okay, and if you can actually write all that in on yours because you don't have a big chunk and pencil like I do on this, then go for it. And now we come to something interesting. I'm going to call this entire thing time interval C, although we could technically break it into a couple pieces, okay? So we'll call this first part right here C sub 1, and we'll call this part right here C sub 2. So what's happening to the object from this point? So it was getting faster and faster and faster, then it was going at a constant speed. Now what's happening to it? It's slowing down, but then it gets to this point. What does it begin to do again? In which direction? In the negative direction. So, well, we could say for this entire thing that during this entire period right here, it is experiencing negative acceleration. Okay? And for C1, we could make the argument that it is slowing down. And then in C2, we could say that it is speeding up. But it's speeding up in the opposite direction because our distance is now beginning to increase. Okay. Time interval D. What's happening here? Well, look at where my curve is going. It's changing direction, right? Okay. So if it has been speeding up, now it is slowing down, right? Which means that it's experiencing what kind of acceleration? Okay. Is it negative? It's positive acceleration. Okay. And it is slowing down again. That finally brings us to time interval E. Flatline. It's dead! No, really, what happened to it? Distance time graph. It stopped moving. Okay? Uh-huh. Okay. Because distance is not changing as time is passing, it has stopped. Now, do you want to know something cool? All three of these graphs tell the same exact story. Look at what's happening down here on our velocity time graph during time interval A. My velocity is increasing, right? But since this is a straight line, I've got constant positive acceleration. Cool. Now look at what's happening here during time interval B. During time interval B, we had written up here, we've got constant velocity because this up here was linear. Well, down here, it's horizontal. So velocity is not changing. It's not getting faster or slower. It's going at the same speed. And then look what we have for all of time interval C. Check this out. From this point here down to this point here, we've got that nice straight line. So we are experiencing, again, negative acceleration through that entire time period. The negative acceleration for the first part causes it to slow down and come to a sort of an instantaneous stop, but it isn't there for hardly any time at all before it begins speeding up again, this time in the opposite direction. Okay, Haley, is your head going to explode?
No, this part makes sense.
Cool. All right, very good. And then during time interval D, remember we said that our object is slowing down, and if you take a look here, look at the direction of the slope. That's positive acceleration, right? And then time interval E, we said it stopped. Well, look at the velocity in time interval E there. It's on the zero line. Yes, it's a constant zero. Yes. And then, oh, check it out, even better. Look down here at our acceleration time graph. Identify for me what parts of the graph, and I'm going to relabel them again. Here's A, here's B, C1, C2, D, and E. Where is the object accelerating? It's accelerating in A. It's accelerating in all of C, and it's accelerating in D, exactly. Where is it going through positive acceleration?
A, C1.
No, C1's negative.
Because see, acceleration is below 0 down here. And we already said this has got a downward slope through all this. And we already said up here for the first half it slows down, then it speeds up. So down here, it's negative. And then where is acceleration not taking place? D and D. Here it's not taking place because it's going at a constant velocity. Here it's not taking place because it's going at a constant velocity of 0. Not so bad when you look at them side by side by side, right? Not awful. Ooh, ooh, ooh. Now, can we put numbers to this?
No.
Oh, we totally can. Yeah, no, but this is not bad, you guys. I promise you. Okay, look here at my velocity time graph. What is, during time interval B, what is this dude's velocity? It's going at about 15 meters per second positive, right? Okay. Let's look down here. What's the acceleration down here during time interval A? Okay, this is 4 meters per second again positive. What's the acceleration during all of time interval C? It's 2 meters per second negative, or negative 2 meters per second squared. Now, look at what this over here shows us. During time interval D, it says our acceleration is exactly the same as it was during time interval A. Okay? And that would make sense. Good.
Teachers, students, pardon the interruption. Teachers, if you have any interest in wanting to collect tickets tonight at our middle school 7th and 8th grade game and JV game, roughly time from 4:30 to 7:30 tonight, please call me in my office. Let me know Coach Morrow is looking for some help. Thank you.
That's money? I can't do it now. I'm sorry.
You got an appointment at 4.
I do have an appointment at 4. You're right. Yes. How do you know?
You said it.
I did. That's right. Thank you. Okay. So what this means, if this right here and if this right here are showing that I've got the same acceleration, then I can confirm that by looking here and looking to see if the slope here is equal to the slope right here. I can't really tell. I'd have to bust out a protractor.
It's equal.
But it looks awfully equal to me. Okay? So, questions? Okay, not too bad. All right, well, I'm going to shut off the video at this point, and I'll put back up my picture of the cheetah and all the graphs on there. I would like y'all to take a look at the back of your page now. And this is going to be something I'd like you to kind of work on, and I would like you to, with the assistance of persons sitting nearby, see if you can complete the data table based on the story they give you, and then see if you can come up with some rudimentary graphs of all 3 types down there at the bottom. Okay?